All right, this should be pretty interesting. We are trying to go over lesson 7.4 from home, so this is the first time I'm going to actually try it this way and using this airliner. We'll have to see how it goes. Hopefully, hopefully you guys will be able to read whatever I write on here. We're going to make this work somehow. Okay, lesson 7.4, exponential growth and decay. This is the first lesson of the two, so this is kind of the introduction. Now, exponential growth and decay is one of the major applications that we're going to use of separable differential equations. So the hardest part is not necessarily the separable differential equation part, because actually that's going to get quite repetitive and you'll see it's the same thing almost every single time we do it. It's understanding what the word problem is asking, because these are all word problems. So let's go ahead and get right to the examples here. You guys can follow along on this thing in your packet. All right. So the first one, population of this little town of Scorpion Gulch is, let's see, it's 1,000 people. The population is presently growing at 5% per year. Write a differential equation that expresses this fact. So it's asking us to write a differential equation. That means we're going to write something with a derivative in it. Solve it and find the equation that expresses the population as a function of time. So let's take this a couple pieces at a time. The population of the little town of Scorpion Gulch is now at 1,000 people, and it's presently growing. Presently growing. So the population is changing over time, because it says some kind of percent per year. So let's see. The population. Here, let's get a pen. Let's do that one. So dp. Ooh, this is going to be interesting. Over dt. I can't do that. Let's erase that real quick. There's just a little bit of a lag that makes this a little difficult to do. Here, let's try it again. Pen. Okay. All right, the population. dp over dt. Wow, this is really not as easy as I was thinking it was going to be. Sorry about that. Try it one more time. dp over dt equals. Now it says the population is changing at 5% per year. So the population is changing at 0.05 times p. Population is changing at 5% per year. Okay. Now it says solve the differential equation and express the population as a function of time. So this is the separable differential equation. We are going to multiply both sides by dt, getting the dt to the right-hand side, and then we're going to divide both sides by p, getting the p to the left-hand side. So what we end up with is 1 over p equals, oh, not equals, not yet. All right, we got to fix this. It's 1 over p dp, forgot my dp, equals 0.05, and then multiplying the dt to the right, we get dt. And at this point, now, we can integrate. Integrate both sides. This is our separable differential equation. Remember that the antiderivative of 1 over p is the natural log of the absolute value of p equals 0.05 t plus c. That is supposed to be, that right there is supposed to be a c. Let's make it look like a c. Plus c. Okay, how do I get the p out of the natural log? We got to exponentiate both sides. So now raising e to the natural log of p. Let's bring this up here. Gives us p equals e to the 0.05t plus c. Remember that that's going to be e to the 0.05t times e to the c, using that property that we talked about. But remember that this e to the c right here is the same thing as just another constant. So we're going to write this as population equals c e to the kt. And if you guys really remember back to when you might have done this before, maybe in pre-calculus or in physics, that's pretty common formula for an exponential growth or decay. Then it says, let's take that equation and use the fact that the town equals 1,000 at time 0 to actually solve for c. So the population is 1,000 equals c e. You're probably asking yourself, what the heck is that k? Good question. That k should not be there yet. Let's get rid of that. The k comes into play much, much later. That should just be t. Actually, not much, much later, but later on in the video. Okay, so we have 1000 c equal c e to the t. Wow, man, I'm just making all kinds of mistakes. Apologize for all this, guys. That should be, this is a lot harder to deal with than I thought. Why isn't the eraser working? Got to be an easier way to do this. There we go. Oops, nope. Eraser. There we go. I forgot the 0.05. Learning curve, 0.05t. Okay, there we go. So down here, I also have to do 0.05t. All right, now let's figure this out. But t, they told us, was 0. So 1,000 equals c e. Now 0.05 times 0 is 0. Don't forget the e to the 0 is not 0, it's 1. So 1,000 equals c times 1, or c. And if c is 1,000, that's what it says to solve for is c. We could actually write the entire population equation as 1,000 e to the 0.05 t. And there you have it. All right, took a while to get through that one, a little over 8 minutes. Didn't mean to make it take that long. Sorry about that. All right, we're going to try and motor through the rest of these pretty quickly here. Number 2, you run over a nail. As the air leaks out of your tire, the rate of change of the air pressure inside the tire is directly proportional to the pressure. That is a key. Let me go ahead and highlight that one because this directly proportional right there, that guy, that's pretty important. If you haven't dealt with direct proportionality before, it really just means that as one thing increases, the other thing increases by some kind of a multiple. And as something else decreases, the other one decreases by some kind of a multiple. If it had said indirectly proportional, that means as one goes up, the other goes down. So they're kind of backwards of each other. They're inverses. So that, again, is very important. And it just means we're going to have to introduce some kind of a multiple. And typically that multiple is called k. So you'll see when we set this up. Write a differential equation that states that fact. Okay, so the air pressure is what's changing over time. So again, we've got dP, this time P stands for air pressure, over dt And that's going to equal some kind of constant K times the pressure. This constant K is very much like the 0.05, which was the rate that they gave us back in the first problem that we did. But we're going to have to find this K this time. And it says evaluate the proportionality constant, just means find the value of K, if the pressure is 35 psi and decreasing at 0.28 psi per minute. This decreasing at 0.28 psi per minute, that's a rate of change. That's dp dt. And because it's decreasing, it's negative. And the pressure at that time, they tell us, is 35 psi. So to solve this for K, we're going to divide both sides by 35, and we'll get negative 0.28 over 35. And you might think to yourself, that right there is something I'm going to have to pull. Whoops, that right there is something I'm going to have to pull out my calculator for. What happened there? There we go. But you don't. Because if you think about it, wow, what's going on here? While I'm trying to find it, if you think about it, what you have is negative 0.28 over 35. If you ignore the decimal point, you've got 28 over 35. Both of them are divisible by 4. So, by 7. 7 goes into the 28 4 times. Sorry about that if you guys can hear my dogs barking in the background. So yeah, 7 goes into 28 4 times, but it's got 2 decimal places, so that's really 0.04. And 7 goes into 35 5 times. Just don't forget it's still negative, and that's K. Now, this, if we want to get rid of the decimal, because it's more common to do that, we're going to move the decimal 2 places to the right, which is really multiplying this by 100, so we'll multiply 100 on the top and the bottom, and you get negative 4 over 500, and that's K. And of course, that simplifies even further. 4 actually goes into both of these things. 4 goes into 500 125 times. So there's K. Better to leave it like this if you can. This one actually works out to be a decimal, which you could use, but sometimes they're not fun decimals to work with, so leave it in an exact form if possible. But there's your proportionality constant. So we've taken care of that. Let's go back up here. All right, and it says solve the differential equation. So we're going to plug the proportionality constant back in for K, and we get that dp dt is negative 1 over 125 p. And then from here, we're going to do the separable differential equation. We'll bring the dt to the right, and we'll divide p on both sides, so we get 1 over p dp equals negative 1 over 125 dt. We are now ready to integrate both sides, and we're going to get the natural log, absolute value of p, equals negative 1 over 125 t plus c. To get rid of the natural log, we exponentiate. E to the natural log of p is p. E to the negative 1 over 25t plus c is, remember, it's e to the negative 1 over 25t times e to the c, but we're going to say that that times e to the c is just some other c. So that's c e to the negative over 125t. There we have it. Man, this lag is rough. Okay? And the bottom one says, now use the initial condition to solve for C. Well, the initial condition says that the pressure is 35 psi at time 0. Well, again, you're not going to have to do this every single time. If you really think about it, the pressure is 35 at time 0. if you were to plug, oops, if you were to plug 0, not 30, in for t, you're going to get e to the 0, which is 1. So if you put 35 in for p, you're going to get that 35 equals c. For what you guys need to know is that c is your initial, that doesn't look good, c is the initial condition. So if they give you an initial condition, you can just plug that right in for the c. So we're going to do that. So p is 35 e to the negative 1 over 125 t. And there's our equation for the air pressure at any given time t. All right, the next couple problems have a couple extra parts. They're not too difficult, but I definitely want to make sure we go through them. The first one, the first couple parts are the same as what we've been doing. So it says bacteria in a lab culture grow in such a way that the instantaneous rate of bacteria is directly proportional to the number of bacteria. Instantaneous rate, derivative. Directly proportional, k times whatever it is. So we're going to start off the same way we have been. dB for bacteria over dt. Okay, that's how the bacteria is changing, is directly proportional, k, to the bacteria, b. All right. First one says write the differential equation. We just did. Separate the variables and integrate the equation, solving for the number of bacteria as a function of time. Notice this time they didn't give us any way to find k, so we just have to do this as k as a constant. Multiply the dt to the right, divide the b to the left. 1 over b dB is k dt. Integrate. You guys should be really getting the hang of this part by now. This is going to give me natural log absolute value of b. This is going to give us kt plus c. Exponentiating. Bring that stuff up here. E to the natural log of b just gives us the b. This is going to give us e to the kt times e to the c. So again, it's c e to the kt. And there you have it for part 1. Part 2 says suppose the initial, part B says suppose the initially there are 5 million bacteria. Initially, that's your C. So we'll bring this guy down here. So C is going to be 5 million. 5 goes there. 3 hours later, the number grows to 7 million. Well, now the population of bacteria is 7. So we'll put the 7 there. And it says that happened after 3 hours. Write a particular equation that expresses the number of millions of bacteria as a function of time. Well, the first thing we have to do is find k, but we have everything to find k. And then we can write the general equation as b equals 5e to whatever the k was times t. So in order to do this one, we solve for k. Well, that means we have to divide both sides by 5 because this is an exponential equation, which means we have to get the k out of the exponent of the e. So you have to isolate the e first. That's an e, not a c. There we go. To get the k out of the exponent, well, now instead of doing exponentiation, we have to natural log both sides because the natural log of e to the 3k will get the k out of there. So we'll take the natural log on both sides of the equation. Equals the natural log of e to the 3k. If you remember your properties, natural log says we can take this guy and bring it to the front. That's what we're allowed to do with natural log. So that'll be 3k times the natural log of e. Of course, natural log of e is one of them that I told you guys you need to know, and that's 1. So it's just 3k times 1, which is just going to give us 3k. So we're going to have the natural log, oops, not 1 over. We're going to have the natural log of 7/5 equals 3k ln of e, but I'm not going to write the ln of e because, again, it's just 1. So now to solve for k, we divide both sides by 3, and instead of writing dividing by 3, I'm actually going to say multiplying by 1/3, and the reason that we do that is it just kind of streamlines the k value. Instead of making this big natural log all divided by 3, it just streamlines it in a horizontal fashion. But there's k. It's not pretty, not easy, but there it is. So the bacteria amount is going to be the initial amount, 5e, to the k value, which we found to be 1/3 natural log of 7/5 t. That's the bacteria at any time. So part C wants us to take that equation and says, what will the bacteria population be 1 full day after the first measurement? Well, remember that we're talking about this stuff in hours, because this was originally 3 hours. So 1 full day, of course, is 24 hours. So make sure you plug in 24 for T. So we're going to get B at 24 hours equals 5e to the 1/3 ln 7/5 times 24. All right. You can plug this guy right into your calculator. Just be careful. And you're going to get, what do we get here? That works out to be 73.789. 73.789 bacteria, or that's actually million bacteria. $73.789. Think about that. 73.789 million 1 day after it started, and it started at 5 million. Bacteria spreads like wildfire. That's why so many people get sick so easily. All right, the last part, part D, says when will the population reach 1 billion, which is 1,000 million. So now we're asking the question when. So that means that we're solving for T. So 1,000 is the amount of bacteria, 5e to the 1/3 natural log 7/5 times t. So now to solve for t, it's the same idea as what we did up here when we were solving for k. You got to divide both sides by 5. Dividing 1,000 by 5 gives 200 equals e to the 1/3 ln 7/5 t. And to get t out of here, we're going to take the natural log on both sides. So the natural log of 200, the natural log of all this is going to eliminate the e, so that's just going to give us 1/3 ln 7/5 times t. And then to solve that for t, we're going to divide everything in that parentheses. So instead of dividing by 1/3, I'm going to multiply by 3. So we're going to get 3 ln 200 divided by the ln of 7/5, and that's going to be your t. Now imagine telling somebody, oh, the population is going to reach 1,000 million when the time is 3 natural log of 200 over the natural log of 7/5. Nobody's going to have any idea what you're talking about. So this is definitely something you plug into a calculator to get an actual time that means something to somebody, and it works out to be 47.240, and that's in hours. And that makes a lot more sense because now people can say, oh, that's just a little bit less than 2 days. Think about that. We started at 5 million bacteria. We're up to 1 billion bacteria in less than 2 days. Crazy how fast that stuff spreads. That's why scientists use it to study. It's so easy to study because of that. All right, next example. We have this substance called calculus fluoride. I'm not so sure if that's a real one or not. It's rare though. It reacts in such a way that the rate of change in the amount of fluoride left unreacted is directly proportional to that amount. Again, same idea. I'm going to use F for fluoride. Fluoride is changing over time. Directly proportional is K times the amount of fluoride. Write a differential equation that expresses this relationship and then integrate to find an equation that expresses the amount in terms of time. So again, we got to find the initial expression. So we'll multiply dt, divide by F. And you should notice this pattern is happening every single time. So this is going to give us natural log absolute value of F equals kt plus c. Exponentiating, we get that F is c e to the kt. Eventually we'll be able to just go right to this formula because it's all natural growth, and you'll see that in the next lesson that we do. All right, use the initial conditions. The initial conditions state that the amount is 50 grams at time 0. Well, that's C, so that helps. So F is 50 e to the kt. And it says it's 30 grams when t equals 20 minutes. All right, so it's going to go to 30 grams when t is 20 minutes. Now you can put t in terms of minutes or in terms of hours. You have to choose, but you got to stay consistent. I'm going to go ahead and leave it in minutes. So it doesn't say anything anywhere else that I need to put this in terms of hours or anything. So I'll leave it in minutes. It's just easier. If you're going to put that in hours, 20 minutes is 1/3 of an hour. So again, use 1/3. Don't use 0.33 because it's not exact. All right, let's get this k value. Divide by 50 on both sides. That will give us 3/5 when we simplify. E to the 20k. To get the 20k out, we natural log both sides. Natural log of e to the 20k is just 20k. And then dividing both sides by 20 is like multiplying by 1/20. Natural log of 3/5. There's k. So now to write the final equation for this, F is 50 e to the 1/20 natural log 3/5 t. Good stuff. Okay. Part B says how much fluoride remains after an hour after this reaction starts. Well, remember, we're using minutes, so an hour is going to be 60, so we'll plug 60 in for t. So F of 60 equals, I'm not going to write the whole thing out here. You would plug 60 in for t right there, and plug that stuff into your calculator, and once you do, you should get about 10.8, and I think the units on this thing is milligrams, if I'm not mistaken, by plugging 60 in. So 1 hour afterwards, there are 10.8 milligrams. And again, make sure that it makes sense. At the start, we had 50. 20 minutes later, we had 30, so it's definitely going down. So an hour after that, it should definitely be less than it is. It's 10.8. And then it wants to know how much fluoride is going to, when, excuse me, will it be 0.007. So 0.007 is the new amount. The initial amount, again, was 50 e to the 1/20 natural log 3/5 t. We are solving for t. Okay, so divide both sides by 50. So we get 0.007 over 50 equals e to the 1 over 20 natural log 3/5 t. And again, to get the t out, natural log both sides. So we got the natural log of 0.007. I'm not even bothering simplifying that because we're just going to plug it into a calculator. Equals 1 over 20 natural log 3/5 t. And then we're going to divide by all of this stuff. So we're going to really multiply by 20. And divide that whole thing there by the natural log of 3/5. And that's going to be our t. And again, that means nothing to anybody. So we put that in the calculator. And we get the time is about 347.432 minutes, which is just a little bit less than 6 hours. So it takes about 6 hours to get down to 0.007 milligrams. All right, one more. Hopefully we can get this done about 35 minutes or so. Let's see. All right. Major purchases like cars, houses, and things like that depreciate in value, so this is going to be a decay problem. A reasonable mathematical model for the value of an object depreciates assumes instantaneous rate of change of an object's value is directly proportional to its value. Again, starts it the same way. We'll call it V for value in this case. So the value is going to change, and it's directly proportional to the value. Write the differential equation. Done. Integrate the equation. So we're going to go through the process that we've been doing. So this will be 1 over V dV equals K dt. Integrate. You get the natural log. Absolute value of V is K T plus C. Exponentiate. Kind of running into my second problem here. So exponentiate, we get that V, the value, is going to be C e to the kt. Same thing we've been doing. A little bit different here in part B though. Part B says, suppose that you own a car whose trade-in value is presently $4,200. So that's like the initial value. 3 months ago, it was $4,700. That's interesting. So the current or the time zero value is 4,200 e to the k, and we'll put the t in here in a second. It says that 3 months ago it was 4,700. So that means that the t value actually has to be -3 because it's 3 months in the past. So this is k. Let's make that k a little better. K times -3. So now to solve for k, because we have to get the k value, we have to get the rate, divide both sides by 4,200. See, the two zeros are going to cancel out, so we're going to get 47 over 42 equals e to the -3k. Natural logging both sides is going to give us -3k. And then solving that for k, we'll divide by -3 or multiply by -1/3, which is probably better. So k is -1/3 natural log of 47 over 42. So the particular equation that we're going to have is the value is 4,200. That was the initial value. E to this -1/3 ln 47 over 42. Gets kind of tedious to write. T. That will give us the value of this thing at any particular time. Letter C, again, same idea. What will the trade-in value be a year after the time the car was 4,700? So now let's, again, be careful. At the time the car was 4,700 was 3 months ago. So now a year from that is really 9 months from the time it was 4,200. So it's 9 months from the current C value. So we want to know what will the trade-in value be. So V is going to be 4,200 e to the negative 1/3 natural log 47 over 42. But the t value, again, because now it is actually 9 months from when it was 4,200. It's actually a full year from 4,700. We have to remember that we started, the 4,700 was 3 months in the past. So now we're going to plug that value into the calculator, and the actual value of the car is about 2,997, 2,997.12. And you'll notice that I only went 2 decimal places here because it is money, and typically money is only measured in cents. So it's probably one of the few times you can get away with not using a third decimal place if they ever ask you something that has to do with money. And part D, you plan to get rid of the car when it drops to 1,200. So when is that going to be? The question is when. We're solving for T. So 1,200 is the value that we're going to get rid of it at. 4,200 was our initial value. E to the negative 1/3 natural log of 47 over 42 T. So again, you'll divide both sides by 4,200. We're going to natural log both sides to get the t out of there, and then divide by what's up here. I'm not going to walk you through every step of this process, but the t value works out to be approximately 33.4413 months. So a little less than 3 years, and this thing's going to be worth only $1,200. Unfortunately, it depreciates very quickly. All right, there you have it. It's about 37 minutes. I apologize for it being so long, and learning curve for me too. I'm trying to get used to writing and everything with this new pen from home. So again, hopefully you have enough information, and you'll be able to get the homework done hopefully in class.